Okay, so how do we figure out how much energy is actually being released? So we're on D17 of your workbooklet, and we're going to use Einstein's theory of relativity, which in a nutshell says mass can be converted into energy, and vice versa. And what we find is that a small change in mass actually produces a large release of energy. So the formula in our data booklets, this is on page 8 of the data booklet, is delta E is equal to delta M times C squared. Delta E is the change in energy. And that's going to be in joules. Delta M is the change in mass. And we're going to measure in kilograms. And C is the speed of light. And that's our constant 3 times 10 to the 8 meters per second squared. Okay, so let's take a look at this first example. So in the fission reaction of 1 mole of beryllium-8, the mass of the products is determined to be 2.29 times 10 to the negative 5 kilograms less, so a really small amount, than the mass of the reactants. Calculate the change in energy that corresponds with this change in mass. Identify if this reaction is exothermic or endothermic. So we know it's a fission reaction, so we know it's got to be exothermic. And now we need to write down what we know. So this time they tell us the mass is 2.29 times 10 to the negative 5 kilograms. C is our constant, 3.00 times 10 to the 8 meters per second. We want to know what's our change in energy. So always write out your equation. Change in energy is change in mass times C squared. This is going to be 2.29 times 10 to the negative 5 kilograms times 3.00 times 10 to the 8 meters per second. We're going to square it. So our change in energy is going to be 2.06 times 10 to the 12 joules when we round it out. Okay, so that's one example. So if they give you masses, they could give you the change in mass. They could also give you the mass of the reactants and the mass of the products. And just remember that when we do change in mass, it's the mass of the reactants minus the mass of the products. Okay, and that'll tell us what the change in mass is. Another way that they may tell us is that they're actually going to give us a nuclear reaction. And so you may have to write a balanced equation. You probably won't have to write it from scratch ever, but you may have to balance it out. So this time I'm going to give you the equation. So this is going to be, we're going to do uranium-235 plus 1 neutron. It's going to produce 3 neutrons plus barium-141 plus krypton-92. Okay, so now that they haven't even given us a mass in kilograms or grams, we need to figure that out. So we're going to turn in your data booklet to page 8 again, and we're going to use this table here. And what you'll notice is that we have specific nucleotides. So there's barium-141, and they give us a mass. If we look at krypton-92, here's krypton-92. Uranium-235 is down here. And then we have our neutron right here. So we're going to take these mass values, and remember they're all times 10 to the negative 3, and we're going to figure out what the change in the mass of our products and reactants are. Okay, so let's go down here. Oops, that's the wrong page. Okay, so what we're going to do, so we have to use page 8 of the data booklet, and we're going to look up those masses. So the first thing we need to know is the mass of each thing. So mass, and this is going to be times 10 to the negative 3 kilograms. I'm not going to write that out every time. So we're going to add up the mass of our two products. So 235.04392, and remember that's times 10 to the negative 3, plus 1.00866 times 10 to the negative 3. I'll just write them down here so we don't forget. We're going to add those up, and that's going to be the mass of our reactants. Okay, so let's find out what's the mass of the reactants. Add those two up in your calculator, and you should get, and now yours might be different if you have it in scientific notation, but it should be 236.05258 times 10 to the negative 3 kilograms. Okay, so that's the mass of the reactants. On this side, we're going to do the mass of our products. Now, I've got 3 neutrons, and each neutron has a mass of 1.00866. Now remember, times 10 to the negative 3. Plus, I have 1 barium, so barium is 140.91441 times 10 to the negative 3, plus krypton 92 is 91.92611 times 10 to the negative 3. If you take that all up, we are now going to get the mass of the products. And if you plug that into your calculator, again, you'll get some version of this, but I just have mine at times 10 to the negative 3, 8665 times 10 to the negative 3 kilograms. Let me write that a little better. And that's going to be the mass of the products. Okay, so now to figure out the change in mass, we're going to subtract the 2. So take the mass of the reactants, subtract from that the mass of the products, and if you do that in your calculator, you should get 1.8608 times 10 to the negative 4 kilograms. And you'll notice that I haven't rounded. So now, after doing all that work, we can now figure out change in energy. Is the change in mass times c squared, 1.8608 times 10 to the negative 4 kilograms, times 3.00 times 10 to the 8 meters per second. Let's write that a little better. And we're going to square that. And so when you round out your answer, 1.67 times 10 to the 13 joules. And that is a lot of energy. Okay, so there's a workbooklet. There are some practice problems that you can do. These are on page 516. Those would be great. And then as well, there are some, there's a workbook page, page D19, that has a whole bunch of problems as well that you can work on.